last video for this unit is looking at machines and what they're able to accomplish. So the first question is, what is a machine? It's a device that makes doing work easier. Now remember to consider work in the sense of the scientific definition and the equation. And we know machines can be very simple. We've got levers and inclined planes, and we put them to practical use in the form of knives, scissors, doorknobs, and they make our everyday work easier. But we know machines can be very complex. What we're going to look at is more of how the machines make our work easier. There's three different ways that they can do this. Number one, they can increase the force that can be applied to an object. Humans can only apply so much force, so we use machines to allow a larger amount of force or more newtons to be applied to an object. Another way that machines can make work easier is by increasing the distance over which a force can be applied. And so therefore you're spreading out the work over a longer distance. So less force, if you increase distance, force can go down. And then number three would be changing the direction of the applied force completely to accomplish a certain task. And so when you look at the pictures to the right, you should be able to pick out which one is associated with 1, 2, and 3. And so like number one, when you increase the force, obviously the car jack is the machine that increases the force that can be applied to an object. Now, when you pull down on the lever, you pull down a certain distance. The car only goes up a very short, very small distance. And so when you increase the force, the distance that's going to be allowed for it to move has to go down if you keep work the same. Machines do not do more work. They make the work easier for us. Number two, with the increasing the distance, you can see the inclined plane that increases the distance over which the force can be applied. It would be a lot harder to just pick up that wheelchair versus rolling it over a larger distance. And then the third one, the direction changing, would be the axe at the top. So you apply a force down and it switches the direction of the work in the opposite direction. And so these are very useful tools for us for different jobs that need to be accomplished. Now we're going to look at machines and look at things numerically and with forces. And there's two forces that are involved when a machine is used to do work. First of all, there is the input force, and that is the force that is applied to the machine. That's what the human does. And we use the symbol capital F and then the subscript in, which stands for the effort force or the input force. Now, anytime you have a force, you can associate that if you're applying the force over a distance, you can associate that to the amount of work that can be done. And so humans have to put a certain amount of work into a machine, and we call that the work input, symbolized by the capital W with the subscript in. Then we would look at the output force, which is the second force, which is the force applied by the machine. What did the machine accomplish? And so we'll use the symbol F out for the output force as well as the work out or W out for the work accomplished. And so if you look over here, if you're having the machine do work up a ramp, what the machine actually is doing, what they are accomplishing, the output, is if you would go straight up, that would be what the machine would accomplish. And so let's look at an example and solve for the work input, which is the work done to the machine. If a manager would drag the baseball equipment up a ramp that would be 6 meters long with a force of 80 newtons. And we know that, let me put the drawing thing up here. We know that work, and we'll put in here as a subscript to make my life easier. Work in equals your force times your distance. Well, if you're applying a force of 80 newtons and you multiply that times the distance of 6 meters, we know that the work in is going to be 480, and don't forget the units for work, which is energy, which is joules. So you yourself are expending 480 joules of energy. And so what we'll do later on is look at how that relates to the output to look at how good the machine and is it practical to use a certain type of machine. All right, then we look at machines and how they conserve energy, which means how good are they? Now we know that when a machine is used, some of this energy transferred changes to heat because of friction. And like I said in the other video, we know that engineers are really trying to make machines limit this and make them as efficient as possible. So because the energy that changes to heat cannot be useful or used to do any work, we know that the work output is always going to be less than what we put into it. Machines cannot do more work for us. They just make it easier. And so because of the frictional aspect though, work out what the machine does is always less than what we put into it. Always keep that in mind. Now, there is this ideal world and ideal machine where there is no friction. And so, if there was this ideal world and ideal machine, work in would equal work out. But that is, we know that that's not a practical thing, but that is something that they strive to get as close to as possible. Now, the other, or one of the calculations we're going to do for machines is looking at the mechanical advantage of a machine. And so this pretty much tells you, is it worth using? Is it good? And so it is a ratio that we're going to be dividing of the output force to the input force. Now you can also flip-flop it and divide the input distance by the output distance. Either one works. But here's the equation. You take what you get out of the machine in terms of force, right, and you divide that by what the force that you put into it. Now, remember, we can't do work here because it would never, you can't have more work than, or output work than input work, but you can look at how well or how many more times the machine can increase the force. Now, one example of a machine would be a window blind. And what this does is it changes the direction of the force. You pull down and the machine goes up. And so you're changing simply just the direction. And because of this, the input and output forces are equal. There, it doesn't fly up, it goes up at the same rate that you pull it. And so this mechanical advantage is only one. And so the higher the mechanical advantage, the more advantageous the machine is to use. But we still use window blinds even though they don't have a high mechanical advantage. It depends on the task that we're trying to accomplish. Now here's an example where Susan and Jake's truck gets stuck in the mud and they're using a tree branch as a lever to lift the truck out of the mud. If they apply an effort force of 700 newtons to the branch and the back of the truck weighs 2100 newtons, what is the mechanical advantage of the tree branch lever? So let's take a look. So the equation for mechanical advantage, which is just capital A, or capital M, capital A, that looks awful, that is equal to force out, and I'm just going to write as little as possible here, divided by force in. Now, one of the hardest parts is just knowing which one is which. They give us two forces, 700 newtons and 2100 newtons. Well, remember that the output is what the machine is accomplishing and the input is what you're doing. And so the effort force, which is what you're doing, is going to be the 700. So that's going to go on the bottom. And then what the machine is doing and accomplishing is it's able to lift a weight of 2100 newtons. So let's put those units in there. And when you do that, we divide 2100 divided by 700. We get an answer of 3. Now look at the units because they're the same. Those cancel out and we're left with a naked number. This is one of those instances, pretty rare, but the answer does not have a unit because it's just a number to signify how good it is. And so this has a mechanical advantage of 3, which is a pretty good number. It allows us to accomplish something that we could not do just lifting. Most people cannot just lift the truck by themselves. They have to use that simple lever or that machine. Now let's go on and look at the other calculation that we'll be doing, which is a little bit more useful, which is efficiency. And this is a measure of how much of the work that you put in changes into useful output work. And so with mechanical advantage, what you're looking at is the force or distance and how they compare. This is what you're looking at for efficiency is the work input compared to the work output. And a machine with high efficiency is just going to be much more useful for companies and allow them to make more money, so on and so forth. And so um, that is their goal, is to have the smallest amount of friction as possible so that more of what they put into the machine they can get out of it. And so to calculate the efficiency, we have an equation, of course, and this is a percentage. And so you'll multiply your answer by 100. You'll always get a decimal because you're taking the output work and dividing by the input. Remember, output cannot be larger than the input. And so if it was, you'd get over 100%. And so if you're getting over 100%, that usually means that our calculations are wrong or that you're flip-flopping the output and the input. And so let's look at this in a couple of examples. And so this is just another reminder that we don't have an ideal machine, but if there was, there would be no friction and that the efficiency would be 100%. But even with these windmills, which are very simple looking, the efficiency is rather low. The efficiency of these machines and the windmills are usually only about 20% because a lot of that is friction or turns into friction and sound energy, because that's one of the biggest complaints of those is the amount of sound that they produce and noise pollution. So the efficiency of a real machine, and don't forget this, is always less than 100%. Now, in order to increase the amount of efficiency that a machine can have, what you're going to do is you're going to try to reduce as much friction as possible. And usually this is done by adding a lubricant of some sort, such as oil or grease, and that'll prevent the surfaces from rubbing together as easily. And because the lubricant fills in the gaps between the surfaces, if you remember this picture from before, we looked at this with friction. If you add the oil in there, it's going to reduce the number of microwells, the number of places that the two surfaces are touching to allow them to glide more easily past each other, which when you've got gears in the machines, it really is helpful. Now I have two examples here to run through, and it's very hard for me to write on here. So I'm just going to set this first one up and then we're going to look at it during class. But I do want you to try to get an answer for number one, for this first one, to look to see if you can accomplish it. So a mover is pushing a 90-kilogram box up an incline. So what I would suggest for all of these is you want to always draw a picture, because these do get a little complicated with different numbers. So here you've got your ramp, and then always draw kind of where it is, how far it is above the ground. And so this one is pushing a box up an incline, which is increasing the box's height by 3.1. So here you've got a distance of 3.1 meters. And if the mover is inputting 5,000 joules of energy, well, input means that would be going up the ramp. And so they're giving you joules, which is work. So our work in equals that 5,000 joules. Now, in order to get efficiency, they're asking for the efficiency of this energy transformation. You already have your work in. What you have to do is figure out the output work. And so you need a force, which is going to be the object's weight. And so you're going to multiply the force times the distance and then do the calculation for efficiency.